It is my pleasure and honor to give this talk mostly in honor of Slavek career, as that was planned for May last year. And of course, it was impossible to give it then. And I hope we'll meet again next year, but in the meantime, we can have this event now. So just have a look at the title, which I copied from an early paper by Slavek, and we'll see it in a minute. This is an outlook. I'll talk about mostly 50 years of chaonic atoms experiments and analysis. Early systematics, some confusion with kaon nucleon amplitudes. Confusion has gone, but some problems remain. Then the reality of kaon interaction with two and more nucleons came in. And finally, and this is I'm very happy to do, include some personal remarks. Okay, so this is a paper from, you see, submitted at the end of 1970. So it's probably published early 1971. The interesting point is that I could have met Slavek at that time because I started a sabbatical at the Rutherford lab, 35 kilometers out of Oxford in August 1970. But we have not met. We met many years later and we'll come to it. In this paper, Slavek indicated that in order to handle the data from chaonic atoms, one had really to do the analysis or the physics inside the nucleus. He said that one has to, the K minus Meson interaction within nuclei determine the optical potential, and the Y0 has to be included. That was the name of the lambda 1405 at that time. So this is end of 1970. Middle and end of 1971, two more publications by Bardeen and Torrigoe. Obviously, they are not aware of the work of Slavek, and of course, he couldn't know what they have done. They have done the same, more or less. But here, at the end of 71, just 1 year later, there was already the first data about shifts and widths. Before that, all analysis was confined to calculating the measured ratios of transition. And here, the first time, shifts and widths were mentioned. And this picture, it's a kind of a schematic diagram. You see that the years 70 and 72, between 70 and 72, which I showed in my previous slides, these were the years of change. There were some early measurements of ratios, of intensities, but here really was the beginning and actually the end. This is the whole mass almost of high accuracy measurements of shifts, widths, and yields in 3 different laboratories worldwide. If you sum these numbers, this is 14 and 13, this is 27. It's a little bit more 30, but there are some duplications. So the database today is about 23 or 24 examples. Okay, about 1 decade later, a simple optical model analysis was attempted. And from now on, I will talk only on global large-scale analysis. So this is what we have been doing ever since. We took the whole data, the whole world data, 65 data points. And this is an attempt to do something similar to conventional nuclear physics. So this is a kinematical factor. This is isoscalar. This is isovector parameter, nuclear densities, and see what happens. And we found that this is not needed. I mean, you can feed the data without this. The B0 is, of course, complex. So you have two parameters here. And surprisingly enough, only two parameters, we could achieve 65 data points yielding chi-squared of 2 per point. And considering the simplicity of the model and the fact that the data came from 3 or 4 different experiments worldwide, this is really very good. So conventional nuclear physics, optical potential, that looks very nice, but this should respect the so-called low density limit. At the low density, this should be the scattering length minus the scattering length. That should be, the real part should be minus 0.15. We found plus 63. And here with the imaginary part, we don't agree. And also, this is very important, we found that the geometries of the real potential and the imaginary potentials were different from each other and different from the geometry of the charge distribution. So it was clear that something was not conventional here. Okay, that was the beginning of large-scale fits. About 10 years later, the first K bar N chiral amplitude by Ramos and Osset was tested by Kappa et al. And independently, another amplitude by Chipley et al. Was tested by the so-called Prague-Jerusalem collaboration. And what we found was, taking the amplitudes at threshold, it was terrible. No fit was possible. If we played the changes of 50%, for example, we could get something reasonable. So something was definitely missing. And then we realized that 30 years earlier, at the first paper which I showed you, Slavek had this expression that the amplitude should be taken at the binding energy, which is negative, and some recoil corrections. And because of the importance of the lambda 1405 and the rapid changes that the amplitude undergoes there, that is very, very important. Okay, 10 years later, this collaboration, and you see Alesh is here, and we are here, and Daniel is on the organizing committee, and Iji should be here. We sat together and invented a kind of model. And a model, like every model, has its limitation, but one has to have a model that works. And in this model, we related the amplitude to the energy through the S parameter, and we used simple model, simple physics, general physics, not too many details for the square root of S. The deviation from the threshold is given by the local density, an average density, kinetic energy by Fermi gas momentum, binding energy, real part of the potential, and the Coulomb potential. So we had a kind of algorithm which, for a given density, could give us the elements of the amplitudes. And indeed, that was very successful. First of all, it was very suitable for large-scale fits because it was manageable numerically, reliably used. And here are many additional references. This is only a partial list. And by that time, there were quite a few other models on the market of K minus P, K minus real, imaginary, and similarly for the K minus N. Trouble was that for K minus N, we had to rely really on models because there was nothing really compatible or comparable in the terms of data. Here, of course, they all fit the Siddhartha data and some ratios between reactions above threshold, but they diverge from each other badly below threshold. And at that time, we knew that 10, 20, sometimes 30 MeV below threshold is relevant. So one has to be a bit careful using all that. This is first example of a large-scale fits to the same 65 Kernic atoms data points, which when taken from the potential S is for K minus N with the kinematics, which is implied by all that, is not enough. And we supplemented the amplitudes by a phenomenological amplitude given as function of the local density relative to the nuclear matter density with three parameters, real and imaginary B naught and an exponential. And here, what we could see is we obtain good fits well under 2 per degree of freedom or per point. The real part was well defined and the imaginary part was well defined. And the great thing was that when we tried to use the same approach with the potentials at threshold, always, and for several years we tried it and always we got negative absorptions. And that was an indication that we were really wrong by doing that. Going sub-threshold, all the problems solved, and they all are well-defined and positive. Additional absorption. This is an example. Is it really necessary to go below threshold? An example, just take this at threshold, negative absorption. Do we need Pauli corrections? Yes. Also, we get negative absorption and poor fits. So we could, with this method, we could calculate strong interaction shifts and widths quite reliably. And I want now to focus on the widths in particular. Just note that shifts are small quantities where differences between two large quantities obtained in two separate calculations, with and without strong interaction. Shifts are calculated directly in one single calculation, and if the potential happens to be the sum of two potentials, like chiral potential plus a phenomenological one, then we have here the sum of a single nucleon and a so-called multi-nucleon potential, and we can calculate each one separately. This is the expression. By the way, this is very useful because the width from the eigenvalue can be compared with the width from the integration. And these tests pass to the 5-digit accuracies in our calculation. And this is very reassuring property of these partial widths. What do we know about partial widths? Not much. If we confine ourselves only to bubble chamber experiments, these are 3 experiments mentioned yesterday by Yarka, and we took the single nucleon fraction as 0.75 plus minus 0.05 as an additional information. And indeed, what we found is that calculated ratios indeed vary it's almost flat along the periodic table. A small difference between upper states and lower states, but they from the Prague and the Kyoto Munich potentials, they fit here, and adding the Barcelona potentials, equally good. So with that as an additional, not quite a constraint, but guiding criterion, we could say, okay, we know things quite well, and one should now go further. And now I am around 2015, 16 already and beyond. Try Kn plus Kn potential and see what happens. And we see that we need another phenomenology here. And we just started such tests. This is an example. I'll show you some details in a minute. This is a fit that we add a phenomenology here, and we get chi-squared really acceptable, but negative absorption, which we take it as a rejection criterion. This is another example, another model for Kn plus Knn. The Knn at the moment we take all the Knn come from Barcelona, but it's the question of how we handle them. Anyway, this is an example of accepted combination. We get positive imaginary as expected. The fit is no real deep, well-defined minimum, but the value itself is very, very good. So an interim summary today is the following. If I look very quickly through the 50 years since Slavek's first paper, just phenomenology, we had this fit, which was acceptable, except that one should have said, so what? Okay, we have some fit. Does it fit? Does it combine? Does it connect to anything? The answer was probably not. Threshold single nucleon plus phenomenology, at threshold consistently, all models gave imaginary B negative, which is now a rejection criterion. Subthreshold, this is with the whole kinematics, the whole model that we introduced is really good for nothing unless we add phenomenology, and then we end up with good imaginary potential here. If we try 2 nucleon amplitudes, well, this is not bad, but if we add some additional phenomenology, then we achieve this asymptotic value, and this is probably the way to go. This is in progress, and I know from personal experience that in the next few weeks, there will be some additional good results, but I can't show them here. So I wish to thank all members, past and present, of the Jerusalem-Prague collaboration who shared this journey of understanding the chaotic atom story. But I was asked to say something in addition. This is a quick reminder that we combined also some work with Loiseau and Slavek, where the amplitudes are awfully looking like that, but this is not what I want to talk now. As I told you, I should have, or I could have met Slavek, and I didn't in the 1970s. But when we met, I don't remember exactly when. It was many years later, but it must have been either in Vienna, EXA meeting, Krakow, Meson meeting, or the many meetings in Trento. And in 2007, on my way to the Masurian Lakes conference, we spent the day in Warsaw together with Slavek, and well, people should know what this building is in Warsaw. Some of the must-see pictures in Warsaw. Here is a demonstration that he was there with us. And this is to show that I really was at the Azurian Lake. So this is the most typical picture of Slavic. He's explaining something. I could think of something which is more typical. We found in Slavic something really a very special person. His knowledge is covering everything: European history, culture, politics, and his willingness to share with others is really unique. Once we met before 2007, I mentioned that the family of my mother came from the Masurian Lakes. And you remember that. And when we found ourselves in the Masurian Lakes, he offered to go with me to the same place, just to see the place. And this is a journey that I could not have done on my own, not only because of the language barrier. So he offered to go with us there, and we went. This is to prove that we were there together. And this is the place. This is the town of Suwałki. He has done his homework. You see, for that journey, he came with the notes he took from the internet. First of all, he could verify that the family had a hardware store in that town. That was verified. I had an address that was good until the late 1930s. But Slavic discovered that since then, the name of the street was changed 6 times. Can you imagine? 6 times. Some of them names of important generals. And of course, that is changing with time. So we went there with not knowing if we could find a place. And here we are studying the map, but that was not good enough. This is an attempt by Slavic to find possibly somebody old in an old house who could remember something, but it didn't work out. And so we couldn't locate the address, but seeing the place was very, very good and unique. Slavic, in addition to all his knowledge, turned out to be very knowledgeable and expert on, you see, mushrooms. So my wife collected mushrooms in the Masurian Lakes, and of course, going home by plane, that was not a very good idea. And of course, this is always dangerous, but Slavic assured us that he was an expert, and he took all the mushrooms and told us he was going to make soup that last evening at home. Well, the following day, we checked by internet that it was all right. Mushrooms were okay. And 10 years later, 11 years later, we were happy to host him in Israel. This is the conference dinner at the Panic 2008 conference. This is a unique evening. It is conference dinner in the desert. You can see this is all sand on the ground. It was cold, of course. Desert in the evening is cold. It was windy that day. You can see how people are dressed. And the location is near old King Solomon copper mines, which were active about 3,000 years ago, and not very economical these days. And this is another dinner, not in the desert, but in our home. And you can see Slavic and Agnieszka here. You can see Iji Mares, and of course, some of you might know Gerhard Wagner. So, thank you for your attention, and I just want to say it was an honor to know such a person and scientist and a scholar and a friend like Slavic. Thank you.
Okay, thank you, Eli. Thank you for this nice talk and also for sharing this nice memories of Slavic. So are there any questions about physics or about the memories or comments?
Or about, well, if the question is about mushrooms, address it to Slavic.
Okay, Slavic, what do you have to say?
Well, first, I want to thank Ali for kind words and nice photos, which I do see for the first time.
I'll send you all of them. I'll send you even more.
Oh, that is again my blindness. But I want to continue about my failures. We published a calculation for atomic chaotic level shifts sometime in the mid-70s with Ray Rook. And it was published in Physics Letters. And then a clever experimentalist sent us a note that your optical potential is discontinuous. And that was a clear mistake. And we were shy about this paper anymore. And we never, so to say, attempted another calculation.
Okay.
Thank you, Eddie.
Okay, thank
You're
you.
welcome.
There is a question. Benoit Loiseau, you have your hand raised.
That's right, yes. In fact, my question is not related to physics, but it's related to knowledge or when the meeting with Slavic. So somehow I was ahead of Eli because it happened that I visited on a collaboration. I mean, I was asked to go. I went to Warsaw to discuss with our colleague Lukaszuk and Slavic at the time. So this was, I don't know if it was, I think it's 1976 or 1977. And Slavic, I was with my wife there, and Slavic took us to the top of the Stalin, in quote mark, buildings that Eli showed a picture of this building in his slides. And so he was, okay, so that's the first contact with Slavic. And then afterwards, we met in, as I mentioned in my talk, we met in Uppsala and we started discussing, and that was very friendly and so on. And recently we went in this IN2P3 Coping collaboration. We visited Slavic in Warsaw. So this was in November 2019, 2 years ago. And then we had a chance. I mean, Slavic took us to this new and an impressive museum about Jewish history in Poland. And I recommend people visiting Warsaw to visit this museum. Okay, thank you.
Thank you. Thank you. Okay. Well, are there any more questions or comments? So if not, I think we should be moving on to the next speaker, who is Pavel Moskal. Okay. Whenever you want, Pavel.
Thank you. Thank you. I will try to continue talking about the broad experience and field of research of Professor Wycech. Let me try to share. I hope I am sharing. The screen.
Yeah, everything is fine. Yeah. And now,
Can you?
Yes, but we see it in this, not in the presenter mode, but in the speaker mode. So we see two screens now.
Okay.
Maybe you have to change the view.
So how it is now? Can you?
This is now, this is not in in the presentation mode. Now, perfect. Now, great. Thank you. You can go ahead.
Okay, thank you very much. So it's an honor for me that I was also included into that session to be able to tell you some words about Professor Wycech, who inspired me very much, and I've chosen one of the subjects which is not connected to kaons, something which I learned from the publications of Professor Wycech, and I got fascinated, which was Borromean objects. And this is, in general, one of the part of the research which I was involved in the research center in Jülich at the Cooler Synchrotron COSY, and Professor Wycech contributed to that research a lot, helping us or guiding us on the theoretical side as regards the eta meson interaction with nucleons and nuclei. This is the photo of that facility in Jülich when we did the research, and I will try to show you in a very pictorial way what was the one of the reason to study that eta meson was to learn about the interaction of it with the nucleus of nuclei, and to learn about the mechanism, how it is produced. And for me, it was in a simple imagination, as I will present you from one of my very old transparencies, was whether we will be able to distinguish or to learn to what extent it is produced by resonant, as it is shown here at this animation, when one of the proton is getting excited to the n-star resonance, or whether it goes via the direct production like it is here, when there is no any resonance. And one of the difference, naively thinking, is the size of the interaction region. So I got interested at some moment at the size of the interaction region as an indication of the mechanism which is behind the production. And this was after reading an article of Professor Wycech from 1996. So you may look at this article. It was the title is simple, so I think that's everything was simple. For Professor Wycech, for me, it was not so simple. A phenomenological model used to analyze the pi and eta meson formation in proton-proton collision. So it was very inspiring paper for me because it was somehow connecting the size of the interactions regions to what we measure as a cross sections. Here is the amplitude from that article. And the article is short. It's like 3 pages, as I remember. And in the center of that page here, you see a Borromean eta proton-proton state. So let's look closer to that. Sentences here. So the enhancement close to threshold, this is what is written there in that article, is due to the strong attraction in the final state, and it may be described by an amplitude of the type 1 with the proton-proton pen produced from an object of about 4 Fermi radius. This is that figure showing a cross-section normalized to the theoretical predictions as a function of the excess energy, and that enhances at threshold. So the question arises, is that a Borromean eta proton-proton state? And this excited me a lot. So I have studied what is a Borromean. Perhaps some of you know, maybe all of you know, but let me recall it. The Borromean state is referred to an object which is built from three constituents and which are bound together, and none of them is bound in pairs. So here is an example, like one could imagine strips of paper, three strips of papers, or three rings of papers, green, blue, and red, and they are bound, so one cannot take out any of this ring by breaking another one. But if you break one, so let's imagine we cut the green one, then you can easily take out blue and red. So in pair, they are not connected or not bound, but as a whole, they are bound. So this is a not only geometrical play for the paper rings, but such objects were found also in nature. So or constructed in nature. So for example, in the chemistry, they have built such molecules, Borromean molecules. But for us in nuclear physics, interesting and an example of such a state is a helium-3 or lithium-11 nucleus. So let's look for helium-6, which is an object which may be imagined as an alpha particle, and two neutrons. And neutron alpha is not bound. Neutron is also not a bound state, but as a three together, they are bound. So this is then the kind of the manifestation of the Borromean state in nuclear physics, or the nuclear in nucleus. So I was excited after reading that paper of Professor Witzech to prove, or maybe to see, whether this eta proton-proton is a kind of such a state. And for that, we have looked for a method to measure the size of the during the production of the in proton-proton eta, that object during the production. And there is a known method called after the names of Harbury, Brown, and Twiss, the correlation frantoscopy. When you look for the momentum distribution of correlated and uncorrelated pairs emitted from the object under the interest. And this we done for this eta meson, but before another expert, Professor Below from Warsaw, calculated for us how such a correlation for this proton-proton eta would look like depending on the size of the system. And here you see that predictions for very large, like 7 Fermi radius, and a small one, 1 Fermi radius. And this were done for few cases. And we have measured that. And here you see the result. So we got something between 3 and 4, about 3.5 Fermi radius. And this was now comparing to that prediction of Professor Witzech, which was 4 Fermi in that article. It was really exciting. But this was the end of that story as regards that size, and we could not find any other way or conceive how to continue to check or to prove whether there is really a kind of the Borromean state. But these results were really exciting, at least for me, when I saw the numbers which were in that article. So our article is from 2010, if you look. So this was like 14 years after that predictions in that paper. So we continue for another looking for another exotic objects or exotic interactions as regards this eta and nucleons. So we are trying to find out whether there is a signal from eta bound to the nucleus via strong interaction. So here you see an examples of the bound states, the gravitational interaction, and electromagnetic. We know atoms, but also the chaonic atoms, which are of interest for us. But what we are looking for, which was this for me new at those days, also under the inspirations and guidance that those days by Professor Wycech, we are trying to look for the eta nucleus bound state. And eta is electromagnetically neutral, so if existed, it must have been bound by the strong interaction. And again, we did that at the studies at this COSY accelerator. And I will show you example of few slides from a typical proposals at the PAG advisory committee, which were presented at those days. Our motivation was that there is a interaction, strong and attractive interaction between eta and the nucleon, which was predicted by Balero and Liu in '85. Then it was by Haider and Liu shown that it may, such a attractive interaction may lead to the mesic, eta-mesic nucleus for A larger than 10. And here are some predictions as an example I've chosen by Eulogio. But what was encouraging for us from Professor Wycech research and discussions was that we may look for such a system also as regards the not necessarily heavy nucleus, but let's look and try to find it out in a light nuclei, like even helium. So we try to do that, and we were looking, assuming a mechanism which you see here as animation, that eta is produced with the helium-4 nucleus, and then this is absorbed by any of the nucleon. Then this resonance is jumping from one to the other nucleon, and then at some moment when it decays into pion, then the system is broken. And such a possibilities of such a measurement were enabled at COSY, at the VASA detector, where we could measure the example deuteron reaction leading to helium with eta, and then this helium-4 could decay into helium-3, which we measured in the forward detector, and this proton and pion pair, which we could recognize in the so-called central detector. And the way of reasoning was to look for the excitation curve, so to look for the number of events. And in that case, we were looking for events like helium, proton, and pion in the final state. And without the production of the mesic nuclei, one would expect, just as this black line here, a constant or this flat distribution as a function of the excess energy. And here is a threshold for the eta helium production. And in case of the production of the bound state, or its existence with the significant cross-section, we would expect such a spectrum with some maximum below or close to the threshold. So this were this is a concept of the experiment. Sorry, I don't know how to take this out. So I am shifting that here and there. And this was the result. Or we did many of these experiments. This is one of the results. You see that excitation curve, and there is no any significant signal of that new mesic nuclei, which would be here on that excitation curve seen as some maximum somewhere, or at least some structure. There was no any significant structure, and the question was, which we were wondering for years, what would be the expectation for such a signal? So in principle, we know it should be some structure, but what should be a cross section for the structure we could expect? And then again, the first paper on that, or first estimation of the cross section, came from Professor Wycech, who predicted based on his calculations here. I will not go into that. That we should expect in that case about a few 4 or 5 nanobars. So at least we knew what is the range of the expectation. So this was for the first time we were not completely blind. But when estimating the sensitivity from that measurements which we did, we could reach the sensitivity which you see here as a upper limits for the creations of such a bound state in that particular reactions. And this was just in the order of the prediction, few nanobars. So we reached the sensitivity of the predictions, but we have not seen, or we could not confirm any signal of that. And then the COSY was closed. So this is kind of the end of this research, at least by us. But we know now that to see such a signal, one would need to increase the sensitivity probably below this few nanobars, at least at the level of 4 nanobars as predicted phenomenologically by Professor Wycech. We could not see a signal. So maybe someday some facility will enable to continue that, but at present this is the kind of the final result we have. And now I would like to show you a few photos which I could collect from the days when I could first time see and meet Professor Wycech. One can unfortunately not see, or maybe you can see that this is the 1991 from the Meson conference photo. This was the first Meson conference, which was organized by, initiated by Professor Jacek, you may see here. This is the conference nowadays Carlo and Catalina are chairing, and it started like 30 years ago. You can see Professor Wycech here. Let me make it larger. So here this is Professor Wycech, and this was like 30 years ago. I will show you the photo from the next year. So it was the next conference, the Meson was in 92. This is a similar photo. Professor Wycech is here to be seen. So let me make it larger. And I especially like that because you may see nothing can change till now. If you look at the photos today, or if we see a talk, it's just the same. What has changed is me a lot. So this is me here. That's what I like that photo, like from the kindergarten. You may compare. There is a difference, but in case of Professor Wycech, we do not see a difference. So this is a photo of like 20 years later for the symposium on mesic nuclei, when we got a lecture what should be done. as regards these measurements we were doing at Jülich. This is from some event during that conference. Again, nothing has changed. So 20 years after the first meson, this is like 16 years after the first meson. And this was from the last meeting we had, the Jagiellonian Symposium. And again, one could see that it was again a lecture. And from the first view, all these events over the last 30 years in Krakow could have been shown as one as regards the lectures of Professor Wycech. At least for me, it's also fascinating. So this is the end of my talk. So thank you, Professor Wycech, dear Professor Wycech, for this really great guidance you gave me and us for the study of the eta meson in nucleon and nucleus system. It was a great honor for me to discuss this physics with you. Thank you very much.
Okay, thank you very much, Pavel, for this nice presentation and also for the memories of Professor Wycech. So at this point, if we have any questions, please raise your hand or talk directly.
Angels?
Yeah.
Avram?
Okay, Avram, go ahead.
Thank you, Pavel, for this nice talk. And congratulations, Slavek, for this meeting that collects traces of your work, which I appreciate very much. I would like to make just two small remarks. One of them, Pavel, the 92 Meson conference meeting, I think I identified Professor Dalitz there in the front line. Is it right? Yeah, and Professor Dalitz was going a lot before the Iron Curtain was raised to communist bloc countries, mostly Poland and also Czechia, because his family, before moving to Australia in the 19th century, came from this part of Europe, and he was looking for the roots of the family. So that's why he also liked to come to meetings where he didn't work particularly on the subject, like on ETA, on other things. And the second remark is not aimed only at you, but just to point out that as I browsed today at the archive new papers, I found out that ELF collaboration in Japan suggested that they see some signal of eta deuterium, but not a bound state, but kind of an excited, a resonant state. So this would be very helpful now to confront with the parameterization that Slavek and others offered for the eta n configuration. So I'd like all of you just to note and to see whether it holds water, as we say. Thank you.
Thank you.
Okay.
Thank you for the comment. Indeed, Professor Dalitz was there. At those days, I didn't know what is a Dalitz plot, and I used it afterwards and learned a lot. But I remember he came, he lost his foils. That at those days we had the foils, as you see here on the, like Professor Wycech was. So this was that projector there, and Professor Dalitz came then with two foils, and at the beginning he told, I prepared that during the night because mine were lost in the plane, and then he asked for the water and poured the water on the foil, and all the talk went out.
Okay.
This is really my recallings from those days as a student.
Okay. Slavek, do you want to talk? Your hand is raised.
Yes, I have two remarks. First to Abraham. If I remember correctly, on one visit of Dick Dalitz in Warsaw, a young man came to help him to find his roots. And if I remember correctly, they found something in the Poznań region, which is northwestern Poland. That's my recollection. The other question which you raised is this ETA deuteron. I was not aware of this Japanese word, but we made calculations some time ago, and we also found that there is no bound state, but there is a kind of virtual state. And the calculation with eta helium-3 was more or less similar, but less certain, that maybe it is a bound state, but rather a virtual state. And that was just a sort of indication that if it is, the binding is so close to helium-3, it should be there in helium-4, but it turned out more difficult. Now, I wish to thank Paweł Moskal for his kind recollection, and I wish to tell that I have bad conscience on the occasion of your collaboration with the Jülich, because I was trying to get a sort of prize for you, and I failed completely. And I still don't understand why, but I failed. It's another sort of failure on my side. Thank you.
Okay.
Thank you. Even more thank you for your support.
Okay. Thank you, everybody. Benoit Loiseau, your hand is raised. Probably is because you forgot to put it down, or you want to say something. Okay. Great. So then we move on to the next speaker of this session, who is Alexander Obertelli.
Hello, good morning, everyone.
Hello.
I will just share my screen.
Great.
Yep. So before I start, I would like to thank very much the organizers for this chance, actually to share with you a context in which a contribution of Sławomir was very important. And this relates to actually what he introduced in his presentation this morning, the study of the nuclear surface, not with kaons this time, but with antiprotons, and namely antiprotonic atoms, as I would like to discuss as a tool for nuclear structure, with a brief review of what was done in the past and how we intend to continue this work with radioactive ions based on the work on Sławomir. So to associated to me, Yuki Kubota, who is working with me, actually was in my group, participated to the conception of these slides, and particularly his work took as a starting point the work of Sławomir, and this is what I will discuss later on. So I will, before speaking of antiprotonic atoms, I will introduce the interest in terms of nuclear structure in studying their surface, and in particular for neutron-rich systems or neutron-deficient systems. Namely, when nuclei have a neutron excess and they are loosely bound, what is called a neutron halo may appear, and this is a quantum effect that a neutron wave function through quantum tunneling may extend very far from the rest of the nucleus, and this is what is called the halo part. Also, they have been discovered already a long time ago at Berkeley by the first experiment by Taniata and interpreted quantum mechanically at CERN by colleagues from Isolde. They are still under active study today, and they have not revealed all their secrets. You can see here on the right the current status of our knowledge of halos. They are known so far for light systems only. As I said, requirements is that they can only occur for loosely bound states. So they are being studied at the drip lines, so neutron halos, but also proton halos have been identified, particularly neon 17 with a large charge radius. In terms of medium mass halos, the knowledge is very scarce so far. I just show here two cases which recently have been claimed to be neutron halos, P-wave halos. Also, this was from a reaction cross-section measurements, and more information is necessary to address this question or to confirm their structure. Recently, actually, even this year, D-wave halos were evidenced or claimed in boron 17, and also the dineutron halos or Borromean systems, as were introduced in the previous presentation by Pavel, actually, are also a field of study, in particular to study neutron-neutron correlations. So I said that the knowledge in medium mass or heavy systems for halos is almost zero. It is the case, and predictions nevertheless show that they are expected to exist also in heavier systems. These are like mean field calculations with a color code, which more or less gives you for the red nuclei the number of neutrons participating to a halo. So you can see that halos are predicted in regions which are unfortunately not accessible so far experimentally, because the neutron drip line today is known up to neon isotopes. And you can see here, for example, if I look at nickel isotope, nickel 78, whose spectroscopy have been performed a few years ago, halos are predicted much further in a region which is not accessible. Nevertheless, moving from stability towards the drip line, another phenomenon is of interest in respect to nuclear surface is the neutron skin, which is an excess of neutrons at the surface of the nucleus, and which is predicted to increase by adding neutrons to isotopes. These neutron skins are often characterized through a quantity which is called the neutron skin thickness, which is nothing else than the difference between the root mean square radius of the neutron radius and the proton radius. They also exist for stable nuclei and are actively studied, in particular in lead-208, which has a large excess of neutrons. And this is justified not only for nuclear physics and nuclear structure, but also for astrophysics, in the sense that there is a very strong correlation between the neutron skin thickness and the nuclear equation of state. This is illustrated here on these calculations for different interactions. The neutron skin thickness for lead-208, the prediction for the neutron skin thickness of lead-208 is compared or plotted as a function of a prediction of the slope factor of the symmetry energy term of the equation of state. Just when the symmetry energy, so the energy density of nucleonic matter is developed as a function of the density, there is a term that corresponds to the asymmetry between proton and neutrons, and this term drives the structure of neutron stars. And this asymmetry energy, when it itself is decomposed as a Taylor development, the first term or the slope term is this L parameter. So somehow measuring with precision in the laboratory the neutron skin thickness or learning about neutron skins tells also about the equation of state, and this justifies many experimental efforts that have been performed in the past and also recently. Just very quickly, there are different methods which are being used to determine this neutron skin thickness, like the measurement of the dipole polarizability of lead-208 from inelastic scattering, proton elastic scattering with large statistics, of course, with the help of an optical potential, which leads to some theoretical uncertainties, is in principle or is used to extract distribution density, which is shown here for lead-208, and therefore be able to give access to a neutron skin thickness. and also electron elastic scattering through parity violation, or gives access to the neutron radius, and also allows to determine a neutron thickness. If one compares these different extractions, one gives an idea of what is the sensitivity of the experiment to this quantity. And you can see that there is a dispersion of results from 0.16 to about 0.3. This is a very recent measurement of this year, a second measurement of the PREX experiment at Jefferson Lab, from a parity violation and also a connection to theory what can extract a weak radius and therefore a neutron radius and therefore a neutron skin thickness. Typically, the uncertainties, as we can see here on this theoretical extraction on the neutron skin, are of about 10 to 30%, essentially from statistics and or model uncertainties. The surface of nuclei has also some other, let's say, points which are under active discussion and unsolved yet. One of them was actually mentioned by Sławomir in his talk this morning, which was the existence of correlations, and in particular cluster correlations in the nuclear surface. And actually, he mentioned this work from Stefan Tippel, which is a theoretical work based on mean field calculations that predict that in the neutron skin there is an onset of alpha clustering. And this was recently backed up by alpha knockout measurement at RCNP in Japan, which compared very well to cross-section calculations based on these estimates. And this was also published this year. Also interestingly, related to neutron skins, there is, to finish with, let's say, the motivations of studying the nuclear surface, there are also some discrepancies between theoretical models of predictions of neutron skin thicknesses. And I show here one example. So what is, this figure is a bit complex. So I just want you to focus on these two different predictions. These are coupled clusters. This is one framework for ab initio calculations, which predicts for calcium-48 a certain neutron skin thickness of 0.13. And this is another prediction, which, okay, this is under debate, but could also be called ab initio. The difference between the two is here the parameters of the model takes also into account data, reaction data. So well, that includes the continuum. These predictions give a neutron skin thickness of 0.25, which is much larger. So there are still among models also even so-called ab initio models, depending on how or constrained the parameters, rather large discrepancies between the prediction. So in this context, and this was the claim in the past and is still the claim, that antiprotons have a large potential, and in particular low energy antiprotons that are captured to form antiprotonic atoms. Indeed, as it was already discussed and illustrated, the annihilation occurs in a part of the nuclear density, which is usually not probed. Let's say most of the probes that I mentioned before, they probe the surface, so around half the saturation density, while the annihilation occurs at about 2 Fermi away from the surface. So this is, in principle, a tool which is complementary to other experimental techniques. And the first studies date from the 70s. Also, most of the work have been performed at CERN from the 19th at the Lear facility. And this is where, in this presentation, at least Sławomir enters, because he made a major contribution in the interpretation of this nuclear structure or nuclear physics experiments with low energy antiprotons. So no need to detail what is the process of the capture. The only point is that I want to make here is that there are 2 different observables which have been used to infer nuclear structure information from this capture. One is the detection of the X-rays from the decay of the antiproton towards the nucleus, and the width of the levels due to the absorption and the lowest levels, and the detection of the residue or the pions resulting from the annihilation. The idea is about the same. is that one can infer the neutron radius from these annihilations. On the first aspect, so by detecting the pions after the annihilation, the electric charge is conserved. And therefore, if one measures the asymmetry between pi minus and pi plus pions, one gets, in principle, an information on the ratio of the neutrons and protons annihilated, which can be connected through theory to the ratio of the proton to neutron density at the nuclear surface, or in the tail of the nuclear density. For the decay, this was also discussed in the previous presentations. Of course, by measuring the width of the last state on which antiprotonic state on which the antiproton is located, this gives a direct information on the nuclear radius under the assumption that the potential is connected to this radius, in this case with a local interaction. So coming back to history, and this I show this presentation with the objective to introduce directly the difficulty of these experiments. So this historical work by Bug et al. In 1973 was based on exactly what I said, by the measurement of the charge pions after the annihilation. And the observable that they measured was the difference of negative pions and positive pions. Okay? And this difference is connected to the excess of neutrons at the nuclear surface. Although there are difficulties, and in particular, the existence of final state interactions is that the detected pions are not the ones which are emitted at the nuclear surface or after the annihilation, but the pions can reinteract with the residual nucleus, and therefore, in the final state, there is a distorted information compared to what one wants to know. And this is actually the work on these final state interactions and the creation of models that can correct from these final state interactions, which is one of the important contributions to the field of Slavonia. Nevertheless, at that time, this was not done. The data was calibrated on carbon-12 data, so assuming that there is a difference of cross-section for the annihilation of neutron and proton, which was equal to the ratio observed in carbon-12, and a certain quantity called the halo factor was extracted from these experiments, which somehow sign the excess of neutrons at the nuclear surface. What is particularly interesting and loops with the physics of halo that we do today is that already in 1973, the term of halo was used to qualify neutron excess at the nuclear surface, well before 1985, for reasons or to describe something which is different from what we call today halo. Okay, so this was more, neutron excess at the nuclear surface. So due to this problem of final state interaction, Lear data were analyzed in a different way. And this is a method which was at the time called radiochemistry. So the idea was not to detect anymore the pions, but to detect or to sign the population of a residue -1 nucleon through its decays. So this is why it is called radiochemistry, with the idea that when only one nucleon is annihilated by the antiproton, this would mean that the pions emitted from the annihilation did not interact strongly with the residue, and therefore the final state interaction is minimized. They could lead either to the nucleus with 1 neutron less or 1 proton less, and this is interpreted in a way that this number of annihilations are sensitive to the neutron density where the annihilation occurred, or to the proton density where the annihilation occurred. The interest of this is this restriction of the data to cold annihilation. This is illustrated here on this plot for nickel 58, where you have density here of nickel 58 as a function of the radius, and the calculation of where, after capture, an annihilation could occur without any restriction on the final state. while by tagging on the final nucleus with only -1, so the annihilated nucleon less, the cold annihilation are predicted to occur further from the surface, so really in the tail of the density distribution. This is performed or is due to let's say a probability function as a function of radius that the pions miss the residual nucleus, and this is just sketched by hand, and this is not calculated, but that I sketch this probability as this shape, meaning that one restricts the annihilation to the tail of the nuclear density in this way. So in these experiments, several experiments were performed at CERN and interpreted in this way, leading to also a neutron halo factor for various stable nuclei, which are actually also correlated to the binding energy. So there was still at the end in the interpretation an ambiguity of the role of the neutron excess, but also the binding energy, because this extraction of the location of the annihilation also had some uncertainties, of course. Another way, as I introduced earlier, to study the nuclear surface, and in particular an attempt also to extract neutron radii, or always in the idea or with the objective to extract neutron skin thicknesses, was to measure with high precision the X-ray transitions from the antiprotonic decay. I give here one example of such a decay, where the shift of the energy of the antiprotonic orbitals compared to QED predictions could be measured of few hundred electron volt, and also a width of the lower level, and one can also deduce a width of the upper level of the last transition, which can be directly related to the optical potential and therefore related to the density, assuming an effective nucleon antiproton scattering length with a real part and imaginary part. You can imagine that there is also here ambiguities or uncertainties related to this extraction of this, the parameters of this potential, which were also fitted on antiprotonic atom data. Nevertheless, these data have produced actually a systematics which could be used to extract neutron skin thicknesses of stable nuclei with a certain medal dependence that I will show here. By assuming a two-parameter Fermi distribution for the proton and neutron densities and fixing the parameters for the proton densities from the, there is a mistake here, I interpolated protons and neutrons, but fixing the parameters from electron elastic scattering, one could deduce the parameters for the neutron density and extract, therefore, a neutron skin thickness, and this is shown here. And these data provided a rather consistent description of the evolution of the neutron thickness, which increased with the neutron to proton asymmetry with a linear dependent as follows. It's noticeable that with the theoretical framework used in this analysis, actually a consistent result were observed from lead 208. You can see that the neutron skin thickness was about 0.14 in this case, which is consistent with most of the other measurements. I will not detail here the effect of the model dependencies. I think, and Slavomir can comment after my presentation, because he is the one who was really active during this time and in this analysis, is that at the end, it was acknowledged that there was a model dependence in this interpretation, but still within the frameworks that were chosen, one could end up with a global consistent picture between the different methods, both with the X-ray analysis and the radiochemical method, and this is illustrated here. What is shown here or the extraction of the neutron to proton density as a function of the radius by use of X-ray data and a certain ansatz for the structure model, of course, and also compared with the halo factor extracted from the radiochemical analysis. And what one can see, and this was in the early 2000s, so after the Lear facility was closed, let's say the last work on the conclusion of these studies. After Lear was closed, I would say that there was a period where antiprotonic atoms were not used anymore for nuclear structure. And my claim here, or what I would like to promote, is that there is now the possibility to restart these studies, not only restricted to stable nuclei, but also to unstable nuclei. And this also gives a chance to improve the framework to analyze this data to be more quantitative. And this would require to revisit actually the proton to neutron annihilation method. So you remember this core method, which was actually the first measurement by Bug, by measuring the pions. Indeed, if one wants to apply or to use antiprotonic atoms with short-lived nuclei which are produced at low intensities, this is the only method at this stage which could lead to enough statistics. Okay. So to remind you, I mean, or to be let's say, to take one example, we assume here one proton antiproton annihilation at the nuclear surface, which leads into, just as an example, a certain decay channel. So proton antiproton, the electric charge is conserved, and you can see here in this particular case we took, to illustrate, 2 pi plus, 2 pi minus, and 1 pi 0. So in this particular case, the sum of the charge is 0, of course, because it is conserved, and the multiplicity of pions, charged pions, is 4. The problem is the following, is that this is not what is detected. What are detected are pions after a potential interaction with the residual nucleus. And in this particular case, one of the pi plus here performs the charge exchange and becomes a pi 0. And you can see that in this case, the detected pions, the picture is different. The sum of the charged pions that can be measured is -1, and the multiplicity of charged pions is 3, so different from what we are interested in principle. And these effects are not negligible, because typically the probability for a pion to reinteract either by being absorbed or by a charge exchange are estimated to, let's say, 10–20%. Okay? The effect of these different processes are illustrated here. If one didn't have a final state interaction, the PP bar annihilation would give a sum of charges of 0, but in reality, what measures in the laboratory is a distribution that depends on all the processes that can change the identity of the pion. This occurs for PP bar, but also for antiproton neutron. Slawomir actually developed the models that are used to determine this final state interaction based on 4 parameters that drive the absorption and the charge exchange of the different pions. And there are actually currently ongoing developments together with Christian to improve these models. But the final word is, if one wants to use this pion emission, one needs to have a fine-tuned statistical analysis to correct from these final state interactions. This was actually proposed by Wada and Yamazaki in 2004 to perform nuclear structure studies with low energy antiprotons and radioactive nuclei based on the tools developed by Slawomir, as I said earlier, with 4 parameters of absorption of the pions and charge exchange. And the main or basic idea, we did not detail it too much, was not to analyze only the total charge of the pions, as was done, for example, by Bug in '73, but to analyze the 2-dimensional matrix of the total charge of the measured pions and their multiplicity. And the idea behind this is that this matrix contains information on the proton to neutron annihilation ratio, but also on the final state interaction. So the objective of the proposed measurement on radioactive nuclei was to use this matrix to disentangle the effect of the proton to neutron densities at the nuclear surface and the final state interactions. And this is actually the basis of the PUMA experiment that we recently was accepted at CERN. So in order to improve this method or to perform this method, I would like to mention a work, which is actually the work of Yuki Kubota.
Alexander, sorry, can you finish in 2 or 3 minutes?
Oh yes, in 2 minutes actually.
Okay, good, thank you.
And the main idea is to actually to implement the neural network to get a model independent or less model dependent approach to extract this final state interaction. So these were benchmarked on intranuclear cascade model, and where we are at this stage today is that the uncertainty on the proton to neutron annihilation ratio after final state interaction correction is 13%. There are a lot of room for improvement, and this is what we are doing now. And our objective is to go below 10%, which is the objective of the PUMA experiment. So the PUMA experiment was actually recently accepted this year. The objective of this experiment is to trap antiprotons at Helena at CERN and transport these antiprotons to Isolde where radioactive ions are produced, and to perform in a dedicated setup, so an ion trap, annihilations after capture of the antiprotons and radioactive ions, and measure the charged pions with a detector inside the magnetic field of the solenoid so that pi plus and pi minus can be disentangled. With this, I finish this presentation, and I would like to thank the PUMA collaborators for this experiment, in particular the members of my group, which are highlighted here, who are working full-time on this project. And I would like to thank very much Slavomir for his contribution and to allow us to have this starting point to make PUMA feasible. Thank you.
Okay, thank you very much for your nice talk, Alexander. And are there any questions that anyone may want to ask right now? Slavek, please.
I was, so to say, pushed by Alexander to say about the model dependence of the previous experiments. And the model dependence is the same which we had with kaons. That with kaons, the ratio of K minus capture on proton to K minus capture on neutron is energy dependent. So it depends on the, so to say, binding separation energy. With the antiprotons, the story is a little bit different. There is dependence of this ratio, but less on the binding energy, but more on the composition of the capture mechanism. Because in antiprotonic case, we have capture in relative S wave and in relative P wave, relative in the antiproton nucleon system. And this ratio depends on the particular situation in nucleus. So this we have to analyze and understand. And I think that PUMA is in much better situation than the former experiments, because it seems that we understand better this ratio. The other advantage of PUMA is that it seems to be less dependent on the final state interaction. So it will measure the neutron radius a little bit closer to the nuclear center. That's what the theorists prefer, because if you ask any theorists, nuclear theorists, they will expect experimental information. They cannot really predict the neutron radius. And if you give them very unclear information about the halo factor or the distribution, they would not look into the results. You have to give them radius mean squared. And that's what will be easier in PUMA, because the experiment depends on higher moments, but we have to offer experimentalists radius mean squared. And that is one of the advantages of PUMA, among other advantages of these experiments. Thank you.
Thank you, Slavek. So is there any other person that wants to say something? I don't see more raised hands. Somebody wants to say something, just activating the microphone? Well, if not, let's thank the speakers, and we are going to go to the next, I'm going to call the next speaker of this session, which is Christian Pisikia. Christian, whenever you are ready.
Thank you. I share my slides. Can you see them?
Yes. You can put it in full screen mode or not. Right now they are not in full screen mode.
Very good. I hope you see. If I put them full screen mode, the problem is now they are, but you don't see them moving, right?
No, at this moment everything is black.
Yeah,
So,
unfortunately. So now you see them.
yeah, okay, let's see.
And
Let's
you
do it
see
like
them
that.
moving.
Okay.
I will try. There were some comments. Unfortunately I didn't try, but I think that you can see them quite big and
yes.
Okay. Thank you. Actually, I reuse the words. I reshape the words of the title of Professor Witzek a bit in my subtitle, because this I choose to speak today was for me a story of instruction and inspiration. And actually, among the various analyses which I had the opportunity, I would say, to follow Professor Witzek, this probably was the most instructive for me, not only because it was the first one, but also because it was quite complicated and challenging. So I really had the opportunity to learn a lot in this work. So it started, I was just recently
Sorry, I don't hear you anymore. Are you Angel's hearing him?
No, I don't hear you. I thought it was my problem, so I was checking if it was me.
No, you had a blackout for half a minute or so.
Yeah, so can you go back a little bit, have a minute, Christian?
Oh, I'm so sorry. Then I will interrupt the video because maybe the band is not so good.
Okay.
Can you hear me now?
Yes.
Okay. So where you arrived? Sorry.
So go back one slide. Yeah, here. Okay. No, here is fine. Go to the next.
Good.
Okay.
So okay. No, at that time I was saying I just discussed my thesis, so I finished my work of PhD, and we met with Professor Witzek and the other collaborators of Amadeus at LNF. And the situation which we told him was quite complicated. We were analyzing this old sample of Chloe data, which was complex because of the disadvantage, but also the advantage of the fact we have a mixture of nuclei, which is involved in each target we are using. Namely, I refer mainly to a mixture of helium, carbon, and hydrogen. And we have two physics, both captures of kaons at rest and in flight. Now, right for the work I just completed in the thesis, we also collected, I needed a sample of reference data, which were pure carbon captures at rest. And okay, when I say in flight, you know very well, in Daphne means a Keon momentum of 100 MeV about, so very small. And the fact that we used Chloe as an active detector a bit more in detail meant that we were using essentially two samples of data, the captures of the kaons in the wall of the DC, which is carbon fiber, so carbon plus a bit of hydrogen, essentially, which comes from the epoxy glue is contained in this material. And the gaseous target is helium in majority, but it also contains a quenching gas, which is isobutane, so again, carbon and hydrogen. So yeah, we have these two physics, so the kaons can be captured both with 0 momentum and 100 momentum, and this was exactly the idea of my maybe first big failure. So I was very happy a few weeks before when I discussed my thesis, because I thought to obtain a very nice fit of the sigma 0 pi 0 spectrum. I was analyzing K- capture in on a bound proton in carbon. And I found that the best fit I obtained was indeed showing, I thought, the evidence for a high mass pole of the lambda 1405. You see that the best fit was 1427 with a quite narrow width. And essentially the idea was exactly to use the flight. So since in carbon the bound proton gives a kinematical mass threshold of 1417 MeV, 16, sorry, MeV, which prevents from observing any 1420 pole of the lambda 1405, I thought, okay, let's use the kinetic energy of the kaon, which gives more about 10 MeV, to open this window, and let's see if there is something. And indeed, as I underlined here with this red circle, we observed something sitting around 1425. I was aware, of course, of the difficulty of the hydrogen. I knew that it was contained in the epoxy, but I made an estimate based on old bubble chamber data captures at rest on hydrocarbons, which gave me a maximum probability of K- hydrogen interactions of the order of 1%. So I thought we were safe, but fortunately, just after discussing with Alessandro, we started to analyze the sigma plus pi minus channel. The sigma minus pi plus was very difficult because of the neutron. So we say, okay, let's take advantage of proton pi 0. Resolution in pi 0 means about 10 MeV, but the resolution on the pi minus is fantastic, is 1 MeV, pi 0, 10 MeV, pi minus 1 MeV. And indeed, when investigating the scatter plot of the pion versus hyperon momentum, we saw in these two data samples a big difference. What I expected in the old data was a superposition of captures on kaon on carbon at rest and in flight, and in the new data just at rest. But indeed, as you can see from the comparison, from the fit we made with the simulation, we discovered a rich contamination of hydrogen, about 20%. I was really disappointed. Then I understood what was my error. Yeah, indeed, when the carbon is captured at rest on, imagine an hydrocarbon, you have a chain of carbons which has a huge electronic cloud, and at rest they dominate on the capture of the carbon. But when the kaon comes in flight, the big number of hydrogen dominates the cross-section. So this was the error. And indeed, the flight contribution of K- hydrogen is very important and distorts the spectrum. You have to consider the fact that the acceptance for all the photons distorts your invariant mass spectrum, and this gives a contribution. Now, in sigma plus pi minus, you can disentangle, is this red distribution, so you can take aware of this. But as we know very well, the cross-section in the charge channel has a contribution from non-resonant isospin 1 component. So here came in this meeting the first brilliant idea of Professor Witzek of the following analysis which we performed. Let's use lambda pi minus channel in which the global resolution for the momentum of the total momentum of the pair is incredible, few MeV, to investigate this non-resonant isospin 1 amplitude and use it in the future as a reference for sigma plus. So I was very disappointed at that moment with this non-resonant contribution, and this was the first lesson he gave me. No, indeed, the non-resonant contribution can be even very interesting by itself. The idea was the following. We knew some data from bubble chamber, K- capture on helium, and we knew that we should have some P-wave amplitude dominated by the sigma star resonance. Since this is very well known, we can pin down the non-resonant contribution. In bubble chamber, the analyses were based on the hypothesis that the reaction is dominated by the direct lambda pi capture, and the residual was treated not contributing to the interaction. They indeed, their analysis indicated hard dominance from the S-wave K-barren capture, which later was also demonstrated by atomic experiments. But also they observed, or Professor Witzek noticed, an excess of events at higher energy, in the kinetic energy of the residual. In the tail, there was a quite rich contribution, which he immediately imagined to be due to the resonant formation, and he immediately understood that indeed the analysis had to be much more careful. First of all, taking into account not only the direct formation, but also the two-step processes in which a primary sigma is produced and maybe some final elastic or inelastic interaction takes over. And also the direct processes are to be carefully analyzed because there are two contributions. One is the S-wave non-resonant, but even if the atomic capture is S-wave, still due to the typical three-body structure of this problem, you can access the resonance. So this is the spectrum which he showed us. And at this point, this is just few months ago, we met for 1 week. Laura invited us in Munich, and we discussed a lot about these ideas together with Oton, Laura, and Professor Witzek. And yeah, he explained us how we took advantage of this idea in this scheme, in which even if the atomic capture occurs from an S-atomic state, you can access by conserving angular momentum the resonance when the K-n interaction is P-wave and the residual is in a P state with respect to K-n. So even if you assume a dominance of S atomic capture, you can still have the contribution from the sigma 1385. Okay, this slide is that because in this period, indeed, I started a collection, which Professor Witzek knows well. Indeed, Oton was joking on me on that period on the fact that I was collecting any note, any piece of paper that he was producing during our meetings, because I was really trying to absorb all the information and studying everything he was producing in our meetings. So we got on the fact that we will redo these analyses based on the data collected by Chloe, and we had to deal essentially with 4 types of processes: the non-resonant direct lambda pi minus production, the corresponding resonant production, and all the kinds of final state interactions, elastic and inelastic. Further, he had another idea. Not only these can be interesting from this dynamical point of view, but also can be used as a comparison for models of K and S-wave interaction. Indeed, we know very well, I go rapidly because this was shown in also yesterday, that in K- proton, thanks to the information given by Siddhartha, we can pin down all the calculation of the real and imaginary parts of the scattering amplitude at the threshold. Below the threshold, still we have some discrepancies, but in K- n, the situation is much more complicated, just because at the threshold we still not have the information given by Siddhartha too. And he imagined already at that time, okay, but we can already give some information using the Amadeus data. And the information that we can give is exactly non-resonant global modulus of the amplitude, obviously, below the threshold, below because we absorb the kaon on a bound neutron in helium. And how much below? Right, the kinetic energy which is available in the K-n center mass system is given approximately by the binding of the absorbing nucleon, minus the kinetic energy which is taken away by the recoil of the lambda pi minus pair with respect to the residual, which he calculated to be about 12 MeV, which is a sigma of 6. Which means, and this is the great idea of the analysis, that the interaction is very short range indeed. So we can use this amplitude essentially as a free parameter of the analysis when we go to compare the calculated probability distribution for the observed momenta with the measured distributions. Also, and last, very interesting is to compare this with what happens above the threshold. So by calculating the non-resonant amplitude from the cross-sections, which were measured at momenta of the kaon greater than 120, indeed he noticed that these were really slightly energy dependent. And so it's extremely interesting to look what happens if we move this downward below the threshold, and with respect to this above threshold measurement, about 55 MeV, which is very of great interest. So this is the phase of the distributions, which he calculated for the S atomic capture and P wave and S wave interactions, so resonant and non-resonant respectively. This C factor is the one which gives this recoupling typical of the S time S to the P time P waves, which open the possibility to the resonance. And yeah, again, the idea was, let's use the resolution, global momentum resolution on lambda pi minus of about 2 MeV to see if we can disentangle these two shapes. Indeed, this is the result of the calculation. And as he taught since the beginning, if you compare the right, which is the resonant, with the left, which is the non-resonant, the mode, the maximum of the probability distribution is shifted of more than 70 MeV. And this went well in the direction to explain the excess of kinetic energy of the residual in the tail, which were measured in bubble chamber experiments. So practically how we realized the measurement, well, you know that in CLOE, obviously, we can measure the position inside the detector of the absorption vertex with a very good resolution. So we can disentangle events in the gas and events in the wall. So essentially events dominated by helium and dominated by carbon. So we measured all the distributions, and we had to fit with a lot of processes. Imagine that we have resonant and non-resonant direct production, both at rest and in flight, but mainly we have a lot of non-direct processes. So the direct production give rise to these red at rest and blue in-flight bands, very correlated momentum plot because it's the direct production. The correlation is totally broken but by whatever final state interaction, elastic and non-elastic. And there were many processes, obviously, because you can produce resonant lambda star or sigma star, or you can go non-resonant directly, and the primary produced sigma hyperon can scatter on neutron, on proton, so many processes to account for, luckily with similar shapes. We also should to account for the possibility of the sigma zero decay in lambda gamma, and he also calculated the contribution of elastic final state interaction of a primary lambda and pion. Luckily, this resulted to give a correction to the amplitude of few percent, at least in the region of the phase space, which we were analyzing. So at some point, we arrived to this picture in which the calculations, all the colors, direct or indirect production of lambda pi, accounted for almost all of the phase space, except you still see some black part. The black points are the data. And this is because, as I anticipated, also in the gas, unfortunately, we have some contribution from isobutane, so captures on carbon. Now, the calculation of the K- carbon is not trivial, essentially because we are not sure of the atomic state of the K- at the capture. But luckily, we could use as one of the components of our fit the measure spectrum in carbon from the sample of K- carbon data, which we had. And from old measurements, bubble chamber of cross-section, we had an idea of how much the carbon should contribute in our mixture. So this is the way we proceeded. We arrived, it lasted quite a lot of time needed to make all these calculations to impose the data analysis. And about 2.5, 3 years after, in this period, we met, me and Magda went to visit Professor Wecek in Warsaw, where we also experienced, I have to say, his and his wife fantastic hospitality. We also went at dinner at his home, and we set the final steps of this analysis, which were, okay, now we are ready. Let's compare the rate of what we expect with the measured resonant and non-resonant production, about 33 MeV below the threshold. So the multidimensional fit, which we decided had these 6 components, indeed at the beginning it was even more complicated because we conceived the possibility that the K- is captured from an atomic P state, but luckily we understood that the contribution of this channel was really negligible in our data. So we remained to disentangle the resonance from non-resonance and all the final state interaction plus the carbon contribution. So let me show you, just to understand what was the goal, the projection into the invariant mass, which is the simpler, obviously, to understand. We had to disentangle this blue curve, which is the sigma 1385, from the S-wave production, which is this wall below the threshold. And yeah, as he thought since the beginning, indeed, the resolution was enough to disentangle them. In the in-flight, unfortunately, we just got a hint. The hint was positive because from this table, if you compare the first 2 numbers are the resonant over non-resonant ratios at rest and in-flight. The resonance in flight is less important, as you see. And this you could expect is good because in flight, the kinetic energy of the kaon moves the energy you have at your disposal in the K- and system just 22 MeV below the threshold. So you are quite farther from the resonance, and indeed we found that the contribution is less. But unfortunately, we are not so sensitive to the flight, so the systematic error was too big to give this second point below threshold. We gave just 1 point, which, by the way, was very interesting. So we found that the non-resonant S-wave transition amplitude modulus in K- n is 0.3 Fermi, which compared with the extracted amplitudes from the measured cross-sections revealed that indeed the amplitude remains constant, almost constant. That does not depend on the energy so much and remains quite flat by passing from above to below the threshold. Lastly, and this plot was already shown yesterday by Albert, so I really spent few words. Yeah, we could compare with the theoretical expectation from the real and imaginary parts. Of course, you have to disentangle because this is coupled channel calculation, so accounting for the other channels which are allowed by the quantum numbers, we obtained this nice situation. Nice because what was at me quite surprising and very good, the global experimental error is comparable, as you can see from the previous table which I showed you, with measurements above the threshold, so it is quite sensitive to the theoretical predictions. So with this I finish. I really would like to express with few words the big gratitude I have to Professor Wecek, and I really wish that this story for me of learning will continue long in the future. Thank you.